Acephysics.org. This presentation is on the kinematic equations of constant acceleration. The kinematic equations are one of the first topics discussed in both college and high school physics. They provide physical intuition about how objects behave under the influence of a gravitational field, as well as anything that moves with constant acceleration, which I didn't write here. They are typically the first example taught in physics where mathematical equations are employed to predict the behavior of the natural world. The equations don't take air resistance into account. They aid in the fostering of intuition regarding vital concepts such as velocity, acceleration, and displacement. On this slide, I present the kinematic equations of constant acceleration. Mechanics is the branch of physics that describes motion on the macroscopic scale. The macroscopic means things that can be seen with your naked eye. For example, an atom. You can't see an atom with your naked eye, so it's not macroscopic, it's microscopic. The kinematic equations describe the motion of objects under constant acceleration. There's only 3 kinematic equations, and I've listed them right here. That makes solving these problems somewhat more manageable because there's only 3 equations to choose from. And I'm going to read through the equations right now. In this box right here, I define what each one of the variables is in words. First equation says x final equals x initial plus v initial t plus 1/2 at squared. The second equation is v final squared equals v initial squared plus 2a delta x. And the third equation is v final equals v initial plus at. And this is really just the definition of acceleration. Acceleration is v final minus v initial over change in time. Here are what each one of the variables is. xi stands for x initial, it's the initial position. xf stands for x final, it's the final position. vi is the initial velocity. vf is the final velocity. A stands for acceleration. T is time. Delta is final minus initial. Little g is equal to the number 9.81. A sub g is negative g. It's negative 9.81. And this is the acceleration of gravity near the surface of the Earth. It's easy to find the derivation for these equations. They're relatively straightforward, although they involve calculus. You can look up the derivation, and it's good to do. However, in order to really gain physical intuition and understand what these equations mean, and more importantly, how things behave under constant acceleration, the most important thing to do is to solve problems involving kinematic equations. So if you want to look up the derivation, you can find it on many, many sites. I'm going to focus on solving problems because on the tests and your homework, you're going to be asked to solve problems. Now what I'd like to do is solve several kinematic equation problems. These problems should cover most one-dimensional kinematic equation examples that can come up. Also, I'm going to first read the problem. A ball is thrown upward with a speed of 38 meters per second from the top of a 240 meter tall building. Part 1. This is a multi-part question. How long will it take for the ball to reach the ground? So first, I wrote down the kinematic equations. Here, because the ball is moving vertically, x is replaced with y. So instead of x final equals x initial plus v initial t plus 1/2 at squared, I have y final equals y initial plus v initial t plus 1/2 at squared. And so there's y's in this equation instead of x's. The first step in any one of these problems is to draw the picture. Here's the picture. There's always going to be an initial point and a final point. There's a building. The building is this red structure. It's 240 meters above the ground. Someone stands on top of the building. They throw a ball upward. This is the initial velocity with 38 meters per second. The ball will travel up. It will slow down as it's moving up, get to its highest point where it's not moving at all. And then it will turn around and speed up as it goes back down. And right before it hits the ground, it's going to have some velocity VF. The question is, how long will it take for the ball to reach the ground? So after you've drawn the picture, you want to write down all the known information, and that's always going to be these variables every time. Y initial, Y final, V initial, V final, acceleration, and time. Then you look at the picture and you just fill in this information. Y initial is 240 meters. It starts out 240 meters above the ground. Y final is at the ground. That's 0 meters. The initial velocity is 38 meters per second. The final velocity, the velocity right before it hits the ground, is unknown, so I wrote a question mark there. The acceleration in the y direction is always negative 9.8 meters per second squared. That's a key concept, and you should memorize that on the surface of the Earth, the acceleration in the y direction is always negative 9.8, no matter what when you're dealing with these type of problems. And time is an unknown. That's what we're looking for. So I wrote it in red. And we want to choose one of these kinematic equations and solve for time. None of the equations will give you the wrong answer, but you won't have enough information to use them all. So you're going to have to choose the correct one to use. The third equation doesn't involve time. And because we're looking for time, we're not going to use the third equation. The second equation does have time in it, but it also has final velocity, and this is something that's unknown. The first equation has all of the information except for time. So that's the equation that we're going to use. So the first kinematic equation is y final equals y initial plus v initial t plus 1/2 at squared. Now let's fill in the information. Y final is 0, y initial is 240 meters, v initial is 38, t is what we're solving for, 1/2 is a number. You replace a with negative 9.8, and then there's t squared. Here I wrote the equation, just putting the t squared term first, the t term second, and then the constant term here. And this is a quadratic equation. The solution for the quadratic equation is negative b plus or minus the square root of b squared minus 4ac all over 2a. A is the term in front of the t squared, in this case, and it can be negative. B is the term in front of the t, and it could be negative. It's not in this case. And c is the constant term. When I plug in all of the information into this equation, it gives me two values. One is negative 4.1 seconds, and the other is 11.9 seconds. The negative time is going to be rejected as spurious, and so it takes 11.9 seconds for the ball to reach the ground. If someone were to throw the ball at 38 meters per second, it would travel to its highest point and come back down and reach the ground in 11.9 seconds. Part 2. How long will it take the ball to reach the highest point? So now, again, you draw the picture, but there's a different initial and final point. The initial point is the same, but now the final point is no longer on the ground. The final point is the highest point, and it's asking for how long will it take for the ball to reach the highest point. You then, once you draw the picture, you then write down all of your variables and fill them in. Y initial is 240 meters. Y final is unknown. V initial is 38 meters per second. At the top of your trajectory in any problem like this, the velocity is 0 at its highest point, the velocity in the y direction. This comes up a lot, and it's something that you should understand as well as memorize. The acceleration in the y direction is negative 9.8 meters per second, and time is unknown. So now we can use the second kinematic equation, which is v final equals v initial plus at. V final is 0, v initial is 38 minus 9.8 times t, and then we'll solve for time, and the time is 3.87 seconds, and that's the answer. Part 3. How long after the ball is thrown will the ball be 265 meters above the ground? So once again, you draw the picture. Here's the ball being thrown from the building. Here's the initial position. And now the final position, the initial position is 240 meters above the ground. The final position is going to be some location 265 meters above the ground. Here are the three kinematic equations. And then let's write down information. Let's write down all the variables. So y initial is 240 meters. Y final is 265 meters. V initial is 38 meters per second. V final is unknown. Acceleration is negative 9.8 meters per second squared, and time is what the question's asking us to find. Because we have all of the information in equation 1, we're going to use equation 1. Y final equals y initial plus v initial t plus 1/2 at squared. Y final is 265 equals 240 plus v initial is 38 times t minus 1/2 of 9.8 is minus 4.9 t squared. I just subtracted 265 from both sides, and then I get 0 is equal to this, which is a quadratic equation. A is negative 4.9, B is 3.8, C is negative 15. You can then plug it in to the formula, the quadratic formula, and the answer is two different positive times. You may want to pause the video right now and ask the question, why are there two times? The reason there are two times is because the ball passes the location 265 meters twice. It passes it on the way up and then also on the way down. So it will take 0.42 seconds for it to go 25 meters upward from 240 to 265, and then it will take 7.33 seconds for it to make this trip and then come back down. 4. What is the velocity of the ball as it reaches the ground? It's very important to know in these problems that this is not the velocity when it strikes the ground. This is the velocity the instant before it reaches the ground. Once it strikes the ground, it will bounce and then eventually stop. That's no longer a situation of constant acceleration, and therefore that can't be described by the kinematic equations. So we're asking for the velocity the instant, right before it hits the ground. First, we draw the picture. Y initial is the same, 240 meters. Now Y final is the ground. It's going to be, because we want to know information about the ball when it's at the ground, but really right before it hits the ground, instantaneously. It's above the ground, but by an angstrom. Now, we want to fill in the information. Y initial is 240 meters. Y final is 0. V initial is 38 meters per second. V final is unknown, and it's in red because that's what the question wants us to find. It wants us to find the velocity at this location. Acceleration is always negative 9.8 meters per second squared in the y direction. And from part 1, we found that the time to go from here to the ground is 11.9 seconds. So I can use the second kinematic equation. V final equals V initial plus AT. V final equals 38 minus 9.8 times t. And this says that the final velocity is negative 78.6 meters per second. The ball starts here. It moves up at 38 meters per second. It will start to slow down. It will get to 0, turn around, and then it starts speeding up, speeding up. Once it gets here, it's going to be going negative 38 meters per second. And then it's going to be going quicker and quicker and quicker. And once it hits the ground, it'll be going negative 78.6 meters per second. What is the velocity of the ball at its highest point? I just want to really emphasize this point, that at the highest point, the velocity of the ball is 0. I already discussed that, but it's so important that, and this is the velocity in the y direction. I really want to emphasize that. How high above the ground will the ball be when it's reached its highest point? So now it's asking for what is this height when the ball reaches the highest point? Again, you draw the picture. Y initial is 240 meters. Y final is unknown, but that's what we're looking for. And then let's fill out all the information that we know. Y initial is 240 meters. Y final is unknown. I wrote it in red because that's what we're trying to find. V initial is 38 meters per second. V final is 0. It's very important that you remember that at the top, the final velocity is 0. Acceleration is negative 9.8. And the time we found from a previous part here, the time to reach the highest point is 3.87 seconds. And so I put time as 3.9 seconds. I rounded. It's really 3.87. Here are the 3 kinematic equations. And now we want to solve for y final. I'm going to choose the first kinematic equation. Y final equals y initial plus v initial t plus 1/2 at squared. You fill in all the information. It tells you that y final is 313.7 meters. Starts out at 240 meters, and it goes up to a total height of 313.7 meters above the ground before it turns around and comes back down. Part 7, what is the average speed of the ball from the time it is thrown until the time it strikes the ground? Average speed is total distance traveled divided by total time. The distance that the ball travels is how far it travels on the way up, and then how far it travels on the way down. The distance on the way up is going to be 313.7 minus 240. That's going to be the distance from the top of the roof to the highest point of 313.7. And then the distance it travels on the way down is the entire distance of 313.7. The time is 11.9 seconds. The average speed is the total distance traveled, which is 387.4 meters divided by 11.9 seconds. And that's, the average speed is 32.5 meters per second. The average velocity is change in y over change in time, which would be y final is 0 minus y initial is 240 divided by the same time of 11.9, and the average velocity is negative 20.16 meters per second. All right, here's another problem. A ball is thrown upward from the ground with a speed of 50 meters per second. What is the maximum height that the ball reaches? What will its velocity be when it reaches the ground? So first question is, what is the maximum height that the ball reaches? You draw the picture. The ball starts on the ground. It moves up to some maximum height, turns around, it comes back down to the ground. Now let's fill out all the information that we know. Y initial is 0. Y final is unknown. That's what we're looking for. V initial is 50 meters per second. V final is 0. This is the highest point. The acceleration is negative 9.8. Time is unknown. Here are the three kinematic equations. We're looking for Y final. We don't know time. The only equation without time in it is the third equation. So I'll use that. V final squared equals V initial squared plus 2a Y final minus Y initial. V final is equal to 0. V initial is 50 plus 2 times negative 9.8 times Y final minus Y minus 0. You can then solve this equation and you see that Y final is 127.5 meters. If you throw the ball upward from the ground at 50 meters per second, it will go a distance of 127.5 meters. When the ball reaches the ground, its speed is negative 50 meters per second. You don't even need to solve anything because this is symmetric. So if you throw the ball upward at 50 meters per second, it will slow down until it gets to its highest point where it's going 0 meters per second, and then it will turn around and start speeding up. And once it gets to the same point it was thrown from, it will have the same speed, but going in the opposite direction. So it's going to have negative its velocity. And so when the ball reaches the ground, really right before the ball reaches the ground, its velocity is negative 50 meters per second. Problem number 3. From the top of a 100-meter tall building, a ball is dropped. At the same time, another ball is thrown upward from the ground with a speed of 50 meters per second. How long after the ball is released will they hit each other? How high above the ground will these two balls hit? You may want to pause the video and try this out.
You're crying.
The first step for any one of these problems is to draw the picture. Here's a building. The building is 100 meters high, and there's one ball, which is blue, which is being dropped. And there's another ball, which I've drawn as red, which is being thrown upward. And at some location and at some time, the two balls are going to hit each other. Let's write down all the information we know for the red ball. Y initial is 0. Y final is what we're looking for. It's unknown. V initial is 50 meters per second. V final is unknown. Acceleration is negative 9.8. Time is unknown. That's the information for the red ball. For the blue ball, Y initial is 100 meters. Y final is unknown, although it's the same Y final as for the red ball because they hit each other at the same location in space. V initial is 0. The ball is dropped from rest, which means you just hold it and let go of it. V final is unknown. Acceleration is negative 9.8. And the time is unknown. The two times will be the same because they meet at the same time. Now what we're going to do is we want to solve for time. So I'm going to use the first kinematic equation for the red ball and fill in all the information. So we have Y final equals 0 plus 50t minus 4.9t squared. Then I'll fill in all the information for the blue ball. Y final equals 100 plus 0t minus 4.9t squared. And I'm going to set these two equal to each other because the Y final, the location in space, is the same for the blue ball and the red ball. And that says that 50t minus 4.9t squared equals 100 minus 4.9 squared. The minus 4.9t squared. The t squared terms will cancel out, and you're left with 50t equals 100, or t equals 2 seconds. So 2 seconds after one ball is thrown, the other one is dropped, they will run into each other. So now we know the time, and now that we know the time, we can find the position by using either one of these equations by plugging in t equals 2 seconds to either one of these equations. So I'll plug it first in to the blue equation. For the blue ball, 100 minus 4.9 times 2 squared. I left off the 0t because 0 times anything is 0, so that term is not there. And that gives us 80.4 meters. And of course, if you plug 2 in for the red ball, you have to get the same answer. And so we have 0 plus 50 times 2 minus 4.9 times 2 squared, and that's 80.